I'm Greg Pfeiffer, founder and CEO of Shine Technologies. Today we're going to talk about a special capability within Building 1, and that's our flare system. The flare system is really important for the world because it generates a uniquely high flux source of high energy neutrons, particularly thermonuclear fusion energy neutrons. Inside this bunker over here is the steady state fusion neutron source we've built, and it's got one of the most elegant tritium facilities in the world as well. This is the operator station where people actually run that machine. So now we're going to be entering the tritium lab, which is immediately before we get to the particle accelerator. One of the things we've learned very skillfully to do here is to manage tritium and process it and keep tritium streams really clean. Including the isotopic separation of deuterium and tritium. This is really the centerpiece of our tritium process. We have to supply clean tritium to the accelerator to maximize the fusion output of the system. This is a really cool system in that, number one, we've managed to do it really cost effectively, and number two, it's extremely capable of separating deuterium from tritium, which is actually necessary to drive the flare business to maximum efficiency, but is also necessary for essentially every near-term fusion power plant design that has a chance of realization. This is the world record holding steady-state fusion neutron source. This beats, to our knowledge, any steady-state sources of fusion neutrons, including national labs, including facilities around the world. It's capable of producing about 50 trillion neutrons per second from deuterium-tritium fusion. It works essentially by accelerating a beam of deuterium particles into tritium gas, and the chamber holding the tritium gas actually is in this pool below me, which is currently empty but would be filled with water during operation. It's obviously very useful for fusion power research, developing components resistant to fusion neutron damage, but it's also extremely important for defense-related work. We want to make sure that satellites are extremely resistant to both nuclear attack and cosmic radiation. The fusion spectrum turns out to be just about perfect for testing the hardness of electronics. So one of the things we're most excited about is just last year, we learned that this has really important implications for national security. And one of the things it can allow us to do is make sure electronics that are part of our defense system will survive a nuclear first strike. We can simulate the effect of a nuclear explosion on electronics components that are meant to keep us all safe. And more importantly, meant to let the bad guys know that if they do something first, we're going to hit them back, right? So the huge number of fusion neutrons made here, again, about 50 trillion per second. So only nuclear fission reactors can produce neutrons of this intensity before we came along. Now this machine that we build in-house can replace nuclear reactors for those applications. And it's proof that fusion has come far enough to replace some nuclear reactors. And so this is a cool machine. It's actually really, really exciting for us to have this, and we're learning about new applications for it all the time. So there you have it, the brightest fusion neutron source in the world, getting us better and better at fusion so one day we can use it to make clean energy and help level up humanity.